In an ideal alternating current system, voltage and current follow a smooth, periodic sine wave. This fundamental frequency, typically 50 or 60 Hz, represents perfect power quality where energy flows efficiently to all connected electrical loads. However, modern electronics like LED lights, computers, and variable speed drives draw current in short pulses. This creates nonlinear loads that distort the original waveform, turning our smooth sine wave into a complex, jagged shape. This distortion is actually the sum of multiple sine waves called harmonics. Harmonics are voltages or currents operating at integer multiples of the fundamental frequency. If our base is 60 Hz, the second harmonic is 120, and the third is 180. According to Fourier analysis, any periodic distorted wave can be decomposed into a fundamental frequency and a series of higher-order harmonics. By layering these different frequencies together, we can mathematically represent even the most complex electrical distortions. We categorize harmonics by their order. In most power systems, odd-numbered harmonics like the third, fifth, and seventh are the most prevalent and problematic, as they tend to reinforce distortion in symmetrical AC waveforms. Total harmonic distortion, or THD, is the standard measurement used to quantify this pollution. It is the ratio of the root mean square value of all harmonic components to the value of the fundamental frequency, expressed as a percentage. Think of THD as a measure of how much the extra frequencies are polluting the main signal. A THD of 0% means a perfect sine wave, while higher percentages indicate significant signal degradation and potential equipment issues. High THD causes serious problems. It increases operating temperatures in motors and transformers due to eddy current losses. This extra heat degrades insulation over time, significantly shortening the lifespan of expensive industrial machinery. Let's calculate the THD for a simple system. If our fundamental voltage is 120 volts, and we measure a third harmonic of 12 volts and a fifth harmonic of 5 volts, we first square and sum the harmonics. The square root of the sum is 13. Dividing 13 by our fundamental 120 gives us a THD of 10.8%. In many industrial standards, this would be considered high, as 5% is often the recommended limit. In three-phase systems, the third harmonic is particularly dangerous. These trip-length harmonics add up in the neutral conductor rather than cancelling out, which can lead to overheating the neutral wire even if the phases are balanced. If each phase has significant third harmonic content, the neutral current can actually exceed the phase current. This is a common cause of electrical fires in older office buildings that weren't designed for modern computer loads. To combat high THD, engineers use filters. A passive filter uses inductors and capacitors tuned to a specific frequency, like the fifth harmonic, to trap that specific frequency and prevent it from entering the main grid. Active filters are more advanced. They monitor the line in real time and inject an equal but opposite current signal to cancel out the harmonics, much like noise-canceling headphones work for sound waves. Standards like IEEE 519 provide guidelines for acceptable distortion levels. For most general systems, a voltage THD limit of 5% is the target to ensure reliable operation of all connected electronic devices. To summarize, harmonics are integer multiples of our base frequency caused by nonlinear loads. THD measures this cumulative distortion. High THD leads to wasted energy, overheating, and potential equipment failure if not properly mitigated. Here is a quick question. If your fundamental power frequency is 50 Hz, what is the frequency of the fifth harmonic? If you calculated 5 times 50, you are correct, the answer is 250 Hz. Understanding harmonics is vital for modern electrical engineering. By monitoring THD and using proper filtering, we ensure a stable and efficient power grid for everyone. Generated by Vision Solve AI.